We present VOODOO 3D volumetric portrait disentanglement for one-shot 3D head reenactment. Our method tackles the problem of creating photorealistic and animatable 3D head avatars from a single portrait image. While many related techniques exist, our focus will be on 3D awareness, which means with consistent output, high-quality identity and expression disentanglement, and robustness to extremely challenging input photos. To animate the avatar, we use expressions and the head pose extracted directly from the driving RGB video. In our case, easier from a webcam. Our 3D aware method is view consistent, therefore ideal for immersive telepresence solutions. Here we showcase this capability using a holographic display which allows two participants communicate remotely in real time in 3D without the need of a headset. This application rendered 25 different views in parallel, requiring 7 NVIDIA RTX 6080 GPUs to ensure real-time performance. Existing one-shot head reenactment methods have the following challenges. 2D head reenactment techniques often produce inconsistencies and artifacts, altering the subject's identity and expressions. This makes them unsuitable for immersive telepresence systems like holographic displays or VR headset. Our method, on the other hand, is 3D aware, as we use a volumetric nerve-based representation to train our model with view consistency in mind. Recent 3D aware head reenactment methods often use explicit 3D face models like 3D meme or plane shapes for expression, pose, and identity disentanglement, but they produce low-dimensional and unnatural expressions. In this work, we represent facial expression implicitly and learn them directly from the data, achieving high realism and fidelity. Our main insight is to introduce an effective pipeline that facilitates fully volumetric approach for expression and appearance disentanglement for head reenactment. Let's walk through our pipeline. Our model has 3 main components: a 3D lifting module, a volumetric disentanglement module, and a volumetric rendering module. We represent 3D avatars as neural radiance views using 3 planes, which work well with deep neural network decoders. We convert 2D images into 3D neural radiance views using a 5-tone version of Epi3D, a state-of-the-art 3D portrait reconstruction model. Next, we perform volumetric disentanglement to extract only the driver expressions and the source identity, independent of the pose, lighting, and expressions of the two. We align the source and driver by rendering them from a frontal view and apply strong augmentations to the driver to prevent identity leakage. Finally, we recombine the driver expression and the source identity into a new reenacted person. We feed these images into a hybrid transformer-based network to calculate a residual that modifies the expression in the source 3 planes. 3D lifting and volumetric disentanglement modules are trained iteratively. To further prevent the identity leakage, we use a proposed cross-identity loss that forces the identity of the output matched with the identity of the source. Finally, we produce coarse renders of the reenacted 3 plane at an arbitrary viewpoint using a volumetric renderer to ensure real-time performance, which is then processed by a super-resolution network to enhance the output fidelity. The output of our method is both realistic and consistent across different views. In addition, the identity of the source image is well preserved. Here are more results of our method. Next, we compare our model against state-of-the-art methods. Our closest baseline is generalizable one-shot head avatar, which is a state-of-the-art 3D head reenactment method that uses parametric models for expressions modeling. While both methods achieve high levels of view consistency, our approach has better expression and identity preservation. More results for comparison can be seen here. Compared to other baselines, we can faithfully reconstruct intricate and complex elements such as hairstyle, facial hair, glasses, and facial makeups. We evaluated the necessity of our 3D lifting fine-tuning strategy. Without it, the 3D lifting module caused severe identity change. Fine-tuning significantly improved the model's identity preservation. We tested a version without frontalization, which failed to transfer the expressions from the driver to the output. The frontalization trick ensures expression-accurate output. We evaluated cross-identity regularization. Without it, the model produced mixed identities of the source and the driver. Our regularization effectively prevents the identity leakage. Lastly, our approach still has some limitations. Those include the inability to model complex mouth expressions, such as tongues. Lacks view consistency for our domain facial accessories, and has no neck pose. We plan to address these limitations in the future. We introduced VOODOO 3D, a new standard for one-shot 3D aware head reenactment. Our method achieves volumetric disentanglement of expressions, poses, and identities, producing superior and consistent outputs while being robust to extreme inputs. Additionally, its computational efficiency enables an end-to-end telepresence system with a holographic display for immersive remote interactions. Thanks for watching.